Today we will talk about shortest path algorithms, Dijkstra's algorithm in particular, and then we'll consider breadth first search, which is, in my view, a special case of the shortest path algorithm. And finally, we'll consider shortest path algorithms that work when edge weights can be negative. All right, so from last class, we introduced Dijkstra's algorithm. By the way, all of these implementation details of priority queue will still be the same. When we evaluate runtime, you'll see the Dijkstra's algorithm runs at the same time that a minimum spanning tree algorithm runs because it's using the same operations. And if we use fancier data structures, we can improve those running times. So we have some designated route A, and we'd like to find the single source, i.e., from source A, we'd like to find shortest paths to all of the other nodes in the graph. If you just were looking... So in the case of, in case you were just looking for the shortest path to a node, to some particular node, you didn't care about the paths to the other nodes in this graph, you would still use this same algorithm and just terminate when you came to node G. So actually what I said is not actually right. Can anybody reason why you can't just stop the first time you get to G? You might actually have a path that had a few extra nodes but had a shorter path. So for example, in the case of I, in the example that we ran through class last time, so remember, the idea of this algorithm is we're going to start with all of the nodes set to distance infinity and the source set at distance 0. And we're going to repeatedly extract min from this queue, take the node that had the smallest distance so far, and then update its neighbors with new distance values. So in this case, we pluck A, and since its neighbors are B and C, we update their distances to 10 and 12. And now B is going to be the node with the smallest distance in the queue, so we extract 10. And we update its neighbors, and we do so throughout the algorithm as such. And if you remember last time, when we came to node I, the first time we came to node I, we updated it to 30. And then right after that, we updated it to 28. So it's not sufficient to just quit as soon as you get to that node. You actually have to run the full algorithm. OK, so this was the actual code, which is on this slide right here. Notice that the only difference between this one and Prim's algorithm is that what we do inside this loop is slightly different. In Dijkstra's, we update if this condition is held, and we update with that value. And in Prim's algorithm, we update with this value right here, just the weight of the edge, whereas in Dijkstra's, we update with the cumulative distance to that node. So the weight plus the distance of the current node. It's a very subtle, simple difference, same implementation. The running time, it was the same as Prim's algorithm. Does anybody remember how that analysis works? So this extract min operation, it's going to take log v time, and it's going to be performed v times. This decrease key operation, it also takes log v time, but it's going to be performed in this loop. Overall, it's going to be performed e time. So the running time of this algorithm, if you use a simple data structure, is again e log v, because this decrease key operation gets called potentially order e times. Okay, so last class, we were stuck on, we stopped class right at the point when we were working out why Dijkstra's algorithm works. So it's not solving a minimum spanning tree problem. We're not going to use a cut theorem for this. We are using the same greedy algorithm, though. How come the same greedy algorithm, or roughly the same greedy algorithm, solves a totally different problem? Why does it work? And the proof of this, which is handed out to you, hopefully you brought it from last class, or if you didn't, you can use today's handout. It's going to rely on these two facts, which I'm just going to state. So the first fact is that the shortest path to a node V can be no larger then the shortest path to some node u plus the weight from u to v. So this is called the triangle inequality because it looks like a triangle like this. This shortest path to v, it can be no worse than going to u and then going from u to v. In other words of saying this is that the shortest path is no larger than any given path. And any given path means you can take any path and break it down into first go to u and then take that last edge from u to v. So keep this in mind as when we talk about negative edge weights, we'll use this fact again. The second property that I want to state is that this value dv, which we maintain throughout the algorithm, we set it here in line 2, we set it to infinity, and then in line 10 of the algorithm, we update it. I'm going to stipulate that this dv is never it's never smaller than delta SV. It's always an upper bound on delta SV. Certainly it's true at the beginning. In line 2, we set it to infinity, and so that makes this property true. And then throughout the algorithm, as we update it, we only decrease it. And when we decrease it because there is some path that gets to that node. And this isn't a proof, this is just the intuition. So by induction, you would prove that, in fact, this property holds. So I'm going to state this is property 1. You actually use property 1 in order to prove property 2. So 2 is the only one we're going to need in the actual proof. So I asked you last class to read and think about this argument. I think I'm going to present it today. So the structure of the argument, we're going to do an induction type of argument, and we're going to maintain a property, an invariant, throughout every loop of this argument. So what we're going to do is we're going to define a set. So set S is going to consist of the nodes that are not in Q. And at line 4, after line 4, S becomes empty because all of the nodes are in the Q. So now we're going to state a property. For all nodes, so the property says for any node in S, in this set S, the value that we've assigned dx, the dx value that we've assigned to that node, is going to be equal to delta Sx. And certainly, P1 holds at line 4. Suppose it holds for the first I iterations of the loop. Consider iteration I plus 1. Now, what is true at this iteration? Node U is removed from Q in line 6. U is the only node that is added to S in this iteration of this loop. It's the only one that we removed from Q. So why does this property hold for node U? Suppose that du is not equal to, so if it is equal, if du is equal to this value, then our property holds and we can complete the proof. So suppose, for the sake of reaching a contradiction, that it's not equal. So what we can claim is that, recall that du is greater than or equal to delta Su. That was our property 2, right? This was by property 2 that we talked about just a second ago. And so now I'm going to say, this implies that there exists some path from S to U. And in last class, I asked you to think about why that was true. Shall we spend 2 minutes with your neighbor thinking about why that should be true? There must exist some path from S to U. Spend 2 minutes with your neighbor, try to explain why that property is true. So these greedy algorithms are kind of tricky. They're subtle. Every example that we've had has this subtlety, and all the 2 homework problems that are greedy will also have this type of subtlety into them. In this case, it's kind of like solving a puzzle. You have a few logical facts, And you just need to concentrate on those facts and put them together in the right way. So here what I'm going to say is that there has to be some path from S to U. Because if there isn't a path, then by definition, delta SU would be infinity. That's what we do when there is no path from S to U. And if delta SU was infinity, that would contradict our equation 1 and 2. Because 1 says du is not equal to that. Okay? So if delta SU is infinity, then du cannot be infinity. And then property 2 says du always has to be larger. And so if du is not infinity, then it has to be smaller, and that would contradict 2. All right? So all we've concluded is that if we come to this point and remove this node, it's either going to equal the distance, or there has to be some path from S to U. If it's equal, if 1 is true, if du is equal to that thing, then our theorem is already proven and we can go home. If it's not, what we've concluded is that there has to be some path from S to U. So let's follow this path. Let's follow this conclusion. So consider any path. Consider any path from S to U. And so I'm going to draw a little diagram right here. So the diagram, it starts at S. And X is the last node in the set S along this path to U. So S to X, X goes to Y, and then Y goes to U in generality. Right? This can be more than one. This can be more than one edge. This right here is one edge, but the rest of them can actually be more than one edge. Okay? I put a dot to indicate that it's exactly one edge. So what can we conclude? The length of this path, it's going to equal. The length of that path is going to be the distance from S to X, the weight of this edge, and then the length of this part right here. And now I'm going to claim that this is equal to, I'm going to claim that this length right here is going to be greater than or equal to dy, because in particular, this right here, this is by the triangle inequality. And this is going to be greater than or equal to du. So these equations are essentially, this last line is the proof. Now I want you to answer, first of all, this first inequality. Why is that true? And this second inequality, why is that true? Well, I guess we have to answer why this one is true as well. All three inequalities. With your neighbor, discuss why they're true. Yeah, question?
Okay. So we go from this to this with the triangle inequality. But, okay, so we have, but doesn't this assume that, like, we know x is on the shortest path of y or something? Because, like, okay, so we've got some shortest path to x, and we add it to y. And then it's clearly going to be less.
There could be some smaller path to y, right?
Oh, wait. So this is, and then, okay, wait, hang on. The part of computer does say dy. Do we actually mean delta sy?
No, that we mean dy right there.
Okay, I think I understand what you're saying. Because we're saying that, okay, this has to be greater than or equal to length than our current best estimate.
Yeah.
Okay.
How do we switch from dy to d? Oh, that first equation. Yeah, I'm asking you why. I'm asking you why dy has to be greater than or equal to du. Yeah.
Why would consider any properties from S to U that has the
We want x to, we know that every x is an s, and so that means that dx is equal to delta sx. So that's how that first inequality, that's why that first inequality is true. Every node in S, by property 1, every node in S has dx equal to delta sx.
So why would it be like that? Why it's not
No, it's the last node along that path, because the next edge from x to y, y is not in S. That's what we want to figure out. Y is not in S. W is for a single weight. Remember, weight is an edge function that maps edges to numbers. So x, y is a single edge, and length is just the length of the path, the sum of the weights along that edge. We could use W along that as well if we want to sort of use, muddle the notation. I was using L for like the length of a path, and W for the weight of an edge. That's what we're trying to prove. Property 1 is saying that D and delta are the same thing for all the things in S. And now we would like to prove it for, we've proved it, we had an invariant. At the beginning of the loop, it's true because S is empty. Suppose it's true for I iterations. Now let's consider the very next iteration we do. Yeah, sorry. So I made a typo. The other thing is also true, but so let's all think about this. dy is larger than du. Why is that? I claim there's a single integer that you can say that will convince me. Not 0. Not 5, not 1. 7. Now why is it 7? Why is it line 7? Perfect. When we have to use every line of this algorithm, otherwise we've got a bad algorithm, right? If we have extra crap in their algorithm that we're not using in our proof, then there's something wrong with our algorithm. That's a good way to check whether you have something right. Line 7 so far hasn't been used in our proof. Well, it seems like we're going to have to use line 7 somewhere. We have to be using a priority queue. Otherwise, line 7 is the main point of using a priority queue. We're pulling the extract min in that line 7, which means that du had to be smaller than dy. That's why this would be true. Okay? And in fact, the way I wrote it was correct. And now I'm going to claim that is true. So that's why this is true. This is because of line 7, extract min. Now why is this one true? Yep. All the weights are negative. All the weights are positive, right? Because L of y comma u is greater than 0. All of our edge weights are positive. And so the length of some path from y to u has to be greater than 0. And this right here is basically our property 2. So we have that the length of P is greater than or equal to du is greater than or equal to delta SU. Okay? And from this I'm going to conclude, why does that follow? We know that du has to be greater than delta SU. That's what we've proved before. And in fact, we're going to use some of the other line numbers for that part of the proof. And now we've showed that the length of P is greater than or equal to du for every single path. This is called a sandwich. So in particular, for that shortest path, right, there's going to be some path for which these two are equal, right? Whatever that shortest path P is, its length is going to be delta SU. That's what it is by definition. And so now, for every path, if LP is greater than or equal to du, then this has to be, that means that du has to equal to this right here. Because in particular, it has to hold for that shortest path. And this contradicts. I'll go back here and put a star. Right. So this star that I put right there is assume, suppose, right? And now, at this point right here, this was the first point we came to, and we said either there's a contradiction or something else has to hold. Okay, well, if that something else holds, we followed that path, and now we've come to another contradiction. So every time we assume that delta u is not equal to delta, that du is not equal to delta su, we've come to a contradiction, and so it must be the case that du is equal to delta su. And then just to finalize the proof, we know that this loop runs v times for every node in the graph, v minus 1 times. And so this must be true for every node in the graph, because at the end of the algorithm, S contains every node in the graph. Right? Because again, line 6, we run until the queue is empty, which means we run until S is full. Did all of those pieces fit? If not, ask me a question on these two slides. Question? So extract min is going to pick the node that has the smallest distance, the smallest key so far. So if I pick du, that means that du had to be smaller than dy. Extract min is a queue, and it is using this dx as the key. Does that answer the question? Question. LP is it's good. It's a notation that I introduced for the length of this path. Similarly, this is the length of y to u. I use w when we're talking about edges. So w, remember, is a function that maps edges to r plus. So this is the weight of an edge. This is the length of this path. This is the length of the shortest path from S to X. More questions?
So if du doesn't add u, why can't you terminate early then once it's part of S? What you said.
That is a good question. Yes, I see. So the point is, you can terminate as soon as that node is, very good question. You can terminate as soon as you remove that, as soon as you've extracted min on that node. And that's very good, because in the example that I was talking about in class, yeah, see, at this point we update it, but we haven't extracted min on this node. So once the node turns gray, you can extract. And that is why I confused my own self, because when I made this statement here, when I made this statement that you could extract, of course, the point is you can extract once you can stop once you've extracted, once that node has turned gray, essentially. Very excellent, excellent point. And this from a student not even in the class. So did everybody get that? You can terminate this algorithm early as soon as that node that you care about has been extract minned. Then, as this proof shows, that means that at that moment, the value you have for the distance is actually the shortest path. Another question. Yeah, L.
Otherwise, wouldn't there be like multiple lengths?
Yeah, L is actually just the sum. The length function is just going to be the sum of the weights along the path from y to u. The reason I use L instead of w is just for notation, because w is supposed to map edges to numbers. This is a thing which maps paths to numbers. And it does so by just adding up the weights along all of the edges in this path. I can't use delta because delta is the shortest path from S to X. without necessarily talking about what that path was. No? All I'm saying is consider any path. Give me the whole path from here to here. You've specified it. So you've specified how to get from S to X, from X to Y, and from Y to U, because you gave me the path. And now I'm talking about what is the length of that path. And I said, well, I can write the length of the path like this, and so forth. Okay. Very good questions. Anything else? Okay, so what I'm saying there, the red one is that one right there. The red one that I'm talking about is that one right there. So this one right here corresponds to this one right here, and this 2 right here corresponds to this 2. So what I'm saying is, if we assume that du is not equal to this number, I'm going to say that at this point it has to imply that there is some path from S to U. And why? Because if there was no path, then delta SU would be infinity. Okay? So what could du be? Du can't be infinity because du is not equal to this, so it can't be infinity. But du is always larger than delta SU. So what could be larger than infinity? Doesn't make sense. No. Let me show you an example. Very good question. I am very thrilled that you guys are asking these things. Consider this graph right here. This is A. It's a graph with no edges. So this I'll set to 0, and these will all be infinity. Right? And now let's run through our Dijkstra's algorithm. Shortest path from A to I. We're going to extract min, and every time we're going to be extracting an infinity. So just because we extract something doesn't mean that there's a path. Good question.
Triangle volumes basically say that the shortest distance.
Well, when edge weights are positive, when the triangle inequality holds, it's saying that the shortest path can't be longer than the path that goes to some node, and then from that node comes to U. So it says that delta SV has to be upper bounded by, for every node in the graph, the shortest path to V has to be upper bounded by the shortest path to U plus the weight from U to V. So some of these can be infinities. If, for example, there's no edge there's no way to fly from Charlottesville directly to Berlin, then that will be infinity. Unless you're John Grisham and have your own private jet. So your question was, is it like saying, the point is there's no notion of a straight line in a graph. So I want to make a connection now between this and breadth first search. Everybody studied breadth first search. I'm sure you've implemented it already in 2150. And the way you should look at breadth first search is that you're trying to find shortest paths when all of the edges, essentially you're finding shortest paths with the constraint that all of the edge weights are 1. So all you're doing is counting the number of edge weights. That's how you should look at breadth first search. Right? So if you start a breadth first search from 0, then it's sort of like sending, another analogy is that you're sending a radio wave from A, and as that radio wave hits nodes, it labels them with their distance from A, right? So something like that. And the thing about breadth first search, I'm sure that you've implemented it. You didn't need a priority queue. All you needed was a queue. And that is a special case of this Dijkstra shortest path algorithm. When all of the edge weights are 1, you can think to yourself how the algorithm that we had, the algorithm on your handout right here, how you can simplify lines 1 through 11 when you know the constraint that edge weights are 1. And it turns out the way you do that is just by using a queue instead of a priority queue. So in this case, I'm sure this is a repeat, but what you do is, if we were starting at node A, you can basically add A to the queue, and then when you pop it off, then you just add the two neighbors of A. So in the next step, you would add B and D and set their distances to 1. And then you'd pop B and then add C and E to this queue as such. A, B, and then D, C, and F. And now you would pop C. And when you pop C, you don't add any nodes. When you pop E, you would add H to the node, and you would set this to 3. You would set this to 3. Okay? And then when you pop F, you would add I to this node, and you would add 3. Right, so everybody see how that works. If we put the code right next to each other, okay? Essentially, the extract min is replaced with the DQ, and the decrease key is replaced with an NQ. Okay? What's the running time of this algorithm? A DQ operation takes how much time? Yep, if you use an array, it just means pull off the top. And a NQ operation takes constant time too, because it just means put it at the back of the array. So both of these operations are order 1. And based on our analysis of those other algorithms, how many times is this called? V. And how many times is this called? So in the special case, when all edge weights are 1, this algorithm runs in order E time. Make sense? Right? If you put this code right next to each other, then in fact, you can sort of see exactly the parallels right there. And the theorem that, breadth first search, the breadth first search theorem is that when you run BFS G comma S, you specify some starting node, then when it terminates, each of the dx that you leave it with is equal to exactly delta Sx when the edge weights are 1. Right, so this is another way of looking at breadth first search. Another way of looking at Dijkstra is to consider breadth first search, except where each of these edge weights, like wherever you have an edge weight of 10, for example, you imagine a silly imaginary path with 10 nodes in between these two nodes. Similarly, here you would imagine 12 little nodes in between. So if you run breadth first search on that node, on that graph, you'll also get the same answer at each of these main nodes. The point is that if you consider this algorithm, this way of computing shortest paths is not efficient because it relies on the weight of it relies on the actual value of these edges. Whereas in a priority queue, you don't have to insert 12. If that edge weight was 12 million, it would be silly to run breadth first search on 12 million nodes that you don't care about, right? So it's just another way of looking at these two algorithms that I know you've encountered before. What else do I want to say? Okay. So now we come to the next use case. So we've talked about graphs in which all of the weights are positive, but there are actually many cases where edges could be negative. This could be, as we see later in this course when we talk about max flow min cut, Or when we talk about reductions, when we consider some problem and reduce it and phrase it as a graph problem and solve that graph problem, this might create edges that have negative edge weights. I'll talk about even an example more specifically. How do we find shortest paths when there are negative edge weights? And in particular, well, let me consider an example first. So this is a classic example of why you want to find why you might have graphs with negative edge weights. So this right here is an exchange. It's an exchange, currency exchange, right? So as of this morning, $1 US is 61.34 Indian rupees and 1.21 New Zealand dollars and so forth. Now, if you are some sort of currency hedge fund trader, what you might try to exploit is the following type of, so you might take $1 US, let's see. This is how Abi might consider making money. We'll see if he's successful. Okay. All right. So what I'm going to do is engage in a series of transactions. So I'm going to turn $1 US into 61 rupees, right? So $1 gives me 61.46 Indian rupees. And now let's see. I'm going to turn 1 Indian rupee into 0.169. So I got to get a calculator here at the same time. So my 61.46 Indian rupees I could turn into no, unfortunately not. So my 61.46 Indian rupees, if I turn those into, let's do New Zealand dollars, 0174. I'll turn that into 1.213 New Zealand dollars. That's basically just multiplying 61.46 by that, 0.01974. And now let's see what we get from New Zealand dollars. We're going to go to Japanese yen. That's going to get me 98 Japanese yen. And now let's get back to US dollars because eventually I want to, and that is going to get me that many US dollars. So this is how I make money, by losing it. You could, of course, imagine that there is some path, some crazy path, which starts with $1 and for a very short moment in time gets you slightly more than $1. And if you find one of those paths, you can just put money into the system. Hopefully you don't perturb any of the prices along the way and eventually end up with slightly more than $1. But of course you wouldn't start with $1, you would start with $10, right? I mean, why waste your time? Really start making some money here. So the way you would model such a transaction, a very nice way is to consider using a graph. And what you might consider is, so you have USD here, and we went to INR, and then we went to NZD, and then we went to JPY, and then we went to USD again. You could imagine a graph with all of the currencies of the world. Okay, and what you're trying to do is find some path that starts at USD and ends at USD, and the length of that path should be, right? These things are all multiplicative. I changed $1 to this, and then the conversion rate here was like this. Yeah, exactly. So what we do is we take the logarithms, right? Because when you take logarithms, now all of a sudden we can reflect this as shortest paths again. Okay? So if we take the logarithms of each of these exchange rates, so this would be log of the exchange rate of India to New Zealand dollars, etc. Now all of a sudden the sum of these weights corresponds to the log of the final exchange rate. Does that make sense, everybody? Yeah? Why do we need logarithms? Because if these were just conversion rates, like, so how did I actually do this conversion? I said this conversion rate was 61.46, right? So I took $1 and I got 61.46. Now, this conversion rate from INR to New Zealand, what did I do it? Yeah, New Zealand dollars was 0.01975, right? And so what I did is I multiplied how many rupees I had by this, right? And that gave me this number. And so every time I convert from one currency to another, I'm multiplying by a conversion rate. That's why I take logarithms, because now that multiplication becomes addition. And once it's addition, I can phrase this problem as a graph problem, as a shortest path problem. The problem is when you take logarithms of numbers like this right here, okay, that logarithm is going to be less than 1. And now that's the motivation for our big problem right here. Because now we have edge weights in this graph that have weight that are negative. Sorry, yeah, when I take logarithms of a number like this, it's going to give me a negative number. Right? Okay. So this is one motivation why we want to study shortest path algorithms with negative edge weights. Another reason is that actually the structure of this algorithm, it's going to be very decentralized. We can run it on many processors at the same time. And so as a result, you can actually use it on the internet, BGP protocol, for example, how packets are routed from here to wherever. It's based on a protocol that's related to this. Even though we know that on the internet there are no negative edge weights for the latency times, we still use an algorithm like this because it has a decentralized structure. You'll see that in a second. First step, where does our old argument break down? Why can't we use Dijkstra's algorithm when edge weights are negative? Why can't we use Dijkstra's algorithm when edge weights are negative? And this, I refer you to this slide right here. Yeah? Yeah. Yeah. In particular, you can even point to some more specific line. This line right here, when we went from du plus this right here is greater than du, that's exact line right there. Underline it, because this is what's violated when this line required that this L right here is positive. And it may not be positive when edge weights are negative. Okay? So I'll draw another, if you saw that picture right there, right? It might be that du was less than dy, and so we try to add u to our set S. Okay? But what if this path was very, very negative, the shortest path from S to u might actually involve taking this treacherous method instead of directly going there. Okay? And that's another consequence of this triangle inequality. First ideas. If I give you a graph with negative edge weights, what's your instinct? Add a constant? So the general strategy, if I give you a graph that has negative weights in it, why don't you make it a graph that doesn't have negative edge weights and then use your previous solution? That sounds like a very good strategy, but it doesn't quite work here. And here's an example. So let's say, okay, so the shortest path from S to U is along this way, right? But it has more edges, 1, 2, 3 edges, 4 edges, 1, 2, 3, 4 edges instead of 2. So if we try to make this a graph that doesn't have any negative edge weights by simply adding 3 to every edge, right, then this will become 4, 4, 0, and 4, and this will become 5 and 5. And so we'll incorrectly conclude that this is the shortest path. And that's because this path only took 2 hops. And so we only added our 3 2 times. Now, of course, you could also compensate. So it's not to say that the strategy is totally broken. You could compensate later by saying, well, this path took this many hops, and this was the weight, and so its actual weight is this. It's not the right answer, and so forth. You can do something like that. And I think the final exam I gave in 2011 had a problem like that. So maybe I will bring that to homework. But instead, we are going to talk about another way to do this. And we only have a few techniques in this class so far. Greedy, it's not going to work here. Dynamic programming, and divide and conquer. Turns out this was the birth of dynamic programming. These type of problems, Bellman and Ford in the 1950s considered these type of problems, and they invented this technique. This is how it started. And so what I'm going to do, the trick to all of these shortest path type of algorithms, is identifying the right variable. And in this case, I'm going to say short IV is going to be the length of the shortest path. Short IV is the length of the shortest path from S to V that takes no more than I hops. With your neighbor, write an equation that describes, so of course to initialize this, short IS, where S is the sink, that's always going to be 0. And short 0, comma V for any vertex is always going to be the length of the shortest path that takes 0 hops from S to V. There is no such path. So it shouldn't be 0, it should be infinity. And so now, finish this off by writing the rest of this dynamic programming equation with your neighbor. Yeah? What is what?
What is triple A B? I assume it's B sort of path, but
Single source, shortest path. Because later on, we're going to do all pairs, shortest path. All right. So there are 2 ways to get to Berlin. Either you're John Grisham and you fly directly in I-1 hops, or you're like me and you fly first through Dulles and then through Munich and then to Berlin. And that means you take I-1 hops to some intermediate destination, and then you take that destination from X to V. So, does that give you a hint on what this should be? The shortest path that takes at most I hops, it's either going to be the shortest path that takes I-1 hops and gets to V, or how would you reflect the length of the path that goes from S to X in I-1 hops and then goes from X to V in 1 hop? Exactly. Does this make sense? Was this intuitive? Question. The I-1. So in order to get somewhere in I hops, what you could do is take I-1 hops and get there, or you can take I-1 hops to get into X and then take 1 hop to get to V. So I-1 plus 1 would be I hops, and so that's certainly a short path that gets from V in no more than I hops. Or you can just directly get to V it might have been the fastest way to just take I minus 1 hops. Yeah? In fact, we will talk. Yeah, so this also solves it for edges. If all the edge weights are positive, this will still work. It'll just take longer, and we're going to see how that plays out. In particular, if I write this into a loop, so this was the equation, and once you have an equation, first of all, you know the length of the path is at most v minus 1, and so the algorithm for this is basically going to be, here, since I'm running out of time. You loop for v minus 1 times, and then in each iteration of that loop, you essentially update this variable. And another way, so look at the way I'm doing this loop right here. In fact, the question you're asking is, what is the runtime of this algorithm? And let's work it out. So I'm going to implement that equation right there. And the way I'm going to do it is for each, I know that the path length is at most v minus 1, so I have to loop I from 1 to v minus 1. And so I need to compute, in particular, I need to compute short of v minus 1v. Okay? And the way I'm going to do that is for each vertex, for each iteration, for each vertex, I'm going to compute this particular set. And notice that this requires looking at all of the neighbors of each v. So just like we did with Dijkstra's algorithm, another way of looking at steps 4 and 5 right here is to change this in order to iterate over all the edges. So in other words, this 4 and 5 loop, it's going to be, for node 1, look at all of your neighbors and compute that function. For node 2, look at all of the neighbors and compute that function. For node 3, look at all the neighbors and compute that function. Another way to do that is to say, hey, let's look at all of the edges. First edge, it's from here to here. Let's update that equation for that first edge. Second edge, let's update the equation for that second edge. So another way to write this loop right here is to write it like this. For I goes from 1 to v minus 1, and then for each edge, update short y based on these 3 values right here. And if you believe that those two loop iterations are exactly the same, they're basically doing the same computation, but in a slightly different order, then the running time of this algorithm is going to be what? How many times does the outer loop run? V. And how many times does the inner loop run? E. Of course, this right here is constant amount of work. So that's the running time of Bellman-Ford, order VE. What was the running time of Dijkstra? And what was the running time of breadth first search? So you see that as the graph becomes more complicated, here, if edge weights are always 1, if edge weights are always positive, if edge weights can be arbitrary values, the algorithm becomes more complicated.
So how can we get the value of short IY while we're determining the value of short IY in that min statement?
Yeah, in this min statement, it's what it is currently. You're currently maintaining it. Yes, you're iteratively improving it. That's right. We will go over this right here next class. So please bring that handout to class again on Thursday.